Hello, in this tutorial I will show you how to create a realistic sniper scope shader in the universal render pipeline using shader graph. As the starting point, we will use our project from my tutorial series. You can download it from my GitHub page. The link is in the description below. First, let's go to the package manager and search for the universal render pipeline package. We can click on it and install it. It will take a while. When it is finished, you can also check if it has installed the shader graph package. It should get installed with the URP package, but if it hasn't installed for you, you can install this package here also. Now, to actually use the universal render pipeline, we have to create a URP asset, and in the project settings under graphics, assign it to the scriptable render pipeline. Now we can see that everything turned pink. It's because we use materials with built-in shaders and not the URP materials. To fix it, we can select all of the materials we use and in the rendering menu, select the option Convert selected built-in materials to URP. Now everything looks okay. But when we start the game, we can see that our bloom effect has disappeared. So how can we fix it? We have to create global volume object. Inside it, we can specify the post-process effects that we want to use. We have to create a global volume profile and add the bloom effect to it. I will set the threshold to 2 and intensity to 5. Then we have to enable post-processing and HDR options in our cameras. Now we can see that our bullets started shining again. For the scope render texture, we also have to change the color format to use 16-bit float values, so it would also support HDR colors. And lastly, we can adjust the emission color on our bullet prefab, so it can be bright enough. I set the intensity on the bullet and trial materials to about 4.5. Now, when we are shooting, we can see that our bullets are beautifully shining again. For the sniper model, I will use a grade 3 asset, which you can find a link to in the description. In the package manager, we can import this asset. After importing it, we can see that all of the materials used in the asset are using built-in pipeline shaders. So let's change them to URP materials. Now we can grab one of the sniper prefabs and place it in our scene. I will adjust its scale and position to fit as a replacement for my old sniper model. Now we can hide or delete our old model and test if the new one works correctly. We can see that this model is very shiny, maybe even too much. So in the materials, we can adjust the material smoothness to our liking. Now it looks better. Now let's get to the scope. Our old scope was octagonal, but it doesn't fit our new round scope. So instead of making a new mesh with many vertices, we will use a simple quad mesh and achieve the round shape using our shader. To do this, we have to assign a quad mesh to the mesh filter and adjust scale and rotation. We also have to remember to fix the scope camera rotation. We won't use the camera scope canvas to display the sniper scope sight anymore, so we can delete it. It's not looking great for now, but we will fix it, trust me. Let's make a new folder for shaders and create our first shader graph shader. We will use an unlit shader because we will create custom lighting. Let's open it. You can right-click to have a shader graph menu pop up and hold a mouse scroll to move around in the shader graph view. First, let's create an UV node and a vector 2 with values x and y set to a half. Then, we use a distance node to measure the distance to our vector, which represents the center. Then we can use 1- node to reverse the effect, so in the center we have 1 and it will decrease to the outside. Then let's create a parameter alpha clip threshold that will control the threshold for the alpha cutoff. Now let's connect our 1- node to the alpha output and our parameter to the alpha clip threshold output. And we can group these nodes and call this group alpha. Let's test it. In our scope material, let's change the shader to our newly created one. And let's tweak the alpha clip threshold value. As you can see, our quad mesh turned into a perfectly round circle, but now our material is white and doesn't show our render texture. Let's fix it. We can create a sample texture node and a main text parameter that will store our texture. Now let's assign main text to the sample texture node and its output to the shader base color output. Okay, so this worked. Let's also do the same thing for our scope side texture. We will create a new parameter and sample texture node. But to mix these textures together, we will use a lerp node, which will take the main texture as input A, scope texture as input B, and scope texture alpha will be the last input that will determine which texture will be used. In that way, the places in which the scope texture is transparent will be filled with the main texture. Now let's connect the lerp output to the base color and see if this works. Let's assign the scope texture, and it works great. Now to add a little bit of realism and add depth to the scope, I wanted it to appear as if the image is inside the scope. So to achieve this effect, we can offset UV coordinates using our view direction in tangent space. We will normalize this view direction, negate it, and multiply by the depth parameter. We will use a tiling and offset node to offset UVs, but first we have to remap it to be in the range from -1 to 1. We can use a remap node to do this. Then we can use param cam scale and apply it to tiling, and then we will remap this back to the range from 0 to 1. Finally, before we apply our new UV values, we will create a new scale and offset subgraph that will use vector4 to store scale and offset vectors. We will split this vector into two vector 2s, remap values to -1 and 1, apply tiling and offset node, and again remap to 0 to 1 values. Now we can use our new node to scale and offset our scope texture. After we increase the depth parameter, we can already see how this texture moves. We can also see how the cam size param works. You can experiment with these values and see what works best for you. Now let's cut our scope texture not to repeat indefinitely. We can use a rectangle node for this and multiply it with the scope texture. Now we can see that our scope doesn't repeat anymore, and we can scale and offset it. To clean up our graph, we can organize our nodes into groups. Now let's create a mask for our scope. We can create a mask scale and offset vector to control the scale and offset of our mask. We will make two options for our mask. One will be using a texture as a mask, the other will be a circular mask. To choose between these options, we will create a toggle use circle mask and use a branch node to lerp between these masks. To create a circular mask, we will calculate the distance to the center point and apply smooth step to it to make a smooth transition between the mask and texture. This smooth step will be controlled by the parameter mask edge. Now we apply this to 1- node and lerp between our texture and mask color based on our mask value. We can create categories for our parameters to better organize them. I will make the mask category to have all mask parameters in one place. Now, when we enable Circle Mask, we can see that our mask works, and we can adjust its edge, scale and color. We can now play with these values and find what will be the best looking. It already looks great, but we are still lacking reflections and lighting. So let's make a getMainLight subgraph. It will output light direction, color, distance attenuation, and shadow attenuation. We will need also 3 custom shader functions, so we will create 3 HLSL files: getMainLightInfo, additional lights, and direct specular. First, in getMainLightInfo, we will create include guards and create our function. It will be called mainLight_half because we will use half precision. It will take as an argument world position and output direction, color, distance attenuation, and shadow attenuation. We can then check if we are in the shader graph preview. If so, we will return some default values. If we are not in the preview, we will check if we are using screen space shadows. If so, we will get shadow chords transforming world position to clip position and then to screen position. Else we can use the transform world to shadow chord function to calculate shadow coordinates. Then we can get mainLightInfo and assign proper values to our outputs. Now we can use our custom function using the custom function node and specifying our inputs, outputs, and function name. We can connect these nodes and save our subgraph. Now let's create the next subgraph. We will call it direct specular. It will calculate specular reflection caused by directional light. It will output specular reflection color. As input, it will take specular color, smoothness value, light direction, light color, and world normal vector. Now we will create our custom function. If we are in the preview, we will output vector 0. Otherwise, we will calculate our output vector using the lighting specular function. Next, we will create calculate main light subgraph that will return diffuse and specular values of the main light. As inputs, it will take specular color, smoothness value, and world normal. We will use our getMainLight node to get mainLightInfo. We will make a dot product from world normal and mainLight direction and saturate the output. Then let's multiply this value with light color, shadow, and distance attenuation. This will be our diffuse value. Then let's use direction specular node to calculate specular value. Let's connect corresponding values and save our subgraph. Now let's make calculate additional lights subgraph. It will also output diffuse and specular values. As inputs, it will take specular color, smoothness, and world normal. Now let's create our custom function. It will take as a parameters specular color, smoothness, world position, world normal, and world view direction, and output diffuse and specular vectors. Now if we are not in the preview, it will loop over all additional lights and sum all diffuse lightings calculated using the lighting Lambert function and all specular lighting using the lighting specular function. After this, we can assign these values to our output parameters. We have to also remember to change the precision to half in the custom function node settings. Lastly, let's make custom lighting subgraph that will combine calculated main light with additional lights. This will output diffuse and specular values and take on input specular color, smoothness, and world normal. Then we will use our calculate main light and calculate additional lights nodes and add diffuse and specular vectors together, and then we output them. Now we can use our custom lighting node in our shader. Let's create a normal map param and assign some example normal texture. We will create UVs for sampling our normal map with scale and offset. And then we will normalize our vector and transform it from tangent space to world space and apply it as a world normal vector. Then we can create smoothness value as a slider and specular color param. To see results of our lighting, we will add specular to our base color. Let's make sure that in all of our custom function nodes, we set precision to half. Now we can test our reflection on the scope. We can see that it works, even if we apply a normal texture. But still, it doesn't have reflections, and this specular can be disturbing when aiming. So we could reduce specular impact when we are close to the scope. But first, let's create reflections. To do this, we will sample a reflection probe using world normal and view direction. Then we will take ambient light, add it to diffuse light, saturate and multiply by our reflection texture. Let's for now swap this with our texture output to see how these reflections look. It is black for now, but as soon as we create a reflection probe, it is displaying its reflection. Now to make these reflections dynamic, we can switch its type from baked to real-time and update it every frame. Then make sure to make this reflection probe a child of our player game object to always follow him. Now this looks great, but our scope isn't useful anymore. So now let's get camera distance to our scope to transition between reflection and scope texture. To do this, we will use a position node and use view space. Then we get the z component of this vector and negate it. To make this transition smooth, we will use smooth step, and we will create a param distance smooth step to control the smooth step slope. Then we will multiply it by reflection strength, so we will be able to control the intensity of the reflection. And we saturate this value to make sure it is between 0 and 1. Lastly, we use this value to lerp between our reflection and scope texture. Let's set reflection strength to 1 to see if this works. We can see that this works great, but still our specular light is quite strong when we are aiming and can be disturbing. So let's also change specular strength based on the camera distance to the scope. To do this, we will create specular min-max parameter and remap distance output to these min and max specular values. Then we can multiply our specular color by this value. In the same way, we can make the normal map more apparent based on the distance to the camera. Now let's organize our nodes into groups to tidy our graph a little. Lastly, I forgot to plug in our new specular value to our custom lighting, so let's fix it. Now let's also clean up our parameters and organize them into categories. We can tweak and experiment with material values, but we can see that our sniper scope looks and works great. Finally, we can add a blur effect to our camera when we are aiming. To do this, we will create a global and scope volume. In the scope volume, we will add a bloom effect and assign it to the new layer Scope Post-Process. Then make sure to select this layer as the volume mask in our scope camera. Next, let's add a depth of field effect to our global volume. I've set the mode to bokeh, focal length to 10 and focus distance to a minimal value. But our focus distance is still too large, so let's modify the minimum value for it in the script. To find this script, you can search depth of field C# script inside packages. Next, let's find the focus distance parameter and change its minimal value. Now we can set our focus distance to 400th. Now it looks okay, but we have blur even if we are not aiming. So let's enable this only when we are aiming. We will modify for this our DOF manager script. We add volume as our param and activate its first element when we are zooming in and deactivate when we are zooming out. Now let's assign our global volume to our DOF manager and make sure that our depth of field effect is the first effect and is disabled at the start. Let's test it. As we can see, it works and looks great. I hope this tutorial helped you and you learned something useful. Thanks for watching and happy coding. Cheers!